Okay, so today at the reading group, we have a guest from the Texas A&M University. So James is a PhD student in the Department of Computer Science at Texas A&M. He's advised by Dr. Guni Sharon. He has a broad research interest in reinforcement learning and multi-agent systems, with a particular focus on the application in traffic control and transportation systems. And I think this talk is in particular on multi-intersection traffic control, right?
Right, thanks.
Yeah. Okay, well, glad to have you today, and looking forward to your talk. Thank you.
Thanks for inviting me. So, like you said, my talk is on multi-agent reinforcement learning and traffic signal control, particularly. First, a quick outline. I'll be discussing traffic signal control as an optimization problem in MDP. Then how this is extended to the multi-agent, multi-intersection setting. I'll then wrap up with a discussion of multi-agent reinforcement learning algorithms designed specifically for traffic signal control and other more general algorithms. Traffic signal control is an optimization problem many of us come face to face with every day. Inefficient controllers cause increased congestion, which in turn produces excess pollution. Studies have shown an incredible volume of wasted time and fuel caused by congestion. In urban areas, congestion due to traffic signal inefficiency may account for up to 55% of delays. So even a small improvement could lead to large benefits to pollution reduction and economic productivity. Classical controllers such as pressure-based and fixed time may in some cases reach satisfactory performance. However, even in these cases, such controllers become increasingly inefficient over time as traffic patterns change due to construction, new routes, and new businesses appear nearby. Recent research has shown that reinforcement learning algorithms may be able to further optimize traffic signal controllers in terms of driving time delays, queue lengths, and emissions. However, when extended to a system of many signals, the domain becomes a challenging multi-agent problem, as we'll see farther on. So before discussing the multi-agent setting, it will be useful to explain how a single intersection is typically modeled as an MDP. Due to sensing assumptions and possible safety constraints, various ways have been proposed to define the state, action, and reward functions. Sensing assumptions range from simple induction loops to complex machine vision algorithms to produce process multimodal inputs, capturing a more complete observation. Static signal controllers, the classical controllers.
Sorry, Arfan, you're not muted. Can you mute yourself, please?
Thanks. The static controllers are unable to leverage the more complete observation provided by camera-based systems, which further motivates the use of reinforcement learning. For this reason, studies of our algorithms often include in the state space the number of arrivals and departures through an intersection. In each lane, aggregate metrics are available, such as the queue length, number of approaching vehicles, and cumulative waiting times. It is also assumed that for each vehicle, the waiting time, speed, acceleration, approximate position, and type can be observed. While at many real intersections, these advanced sensors are unavailable, our goal is to study optimization approaches as they might apply to high congestion intersections, where the benefits of improved performance would outweigh the additional cost of advanced sensors. So in our experiments, we assume the most advanced sensors are available, able to collect all of these features at 200-meter range. So for the action space, we similarly assume the least constrained definition. Actions are given by a non-conflicting pair of phases. By phase, I mean a set of green signals which allow traffic to flow in a particular direction. Conflicting pair of phases, therefore, is one such as the phase 1 in the example here, the picture, paired with phase 2. This pair would assign a right of way to vehicles making a left turn, while also assigning the right of way to vehicles moving straight through the intersection, which would cause a collision. Maybe not immediately, but eventually. So non-conflicting pairs of, for instance, would be phase 1 and 5, or 1 and 6. And there's obviously more than that, but it's just an example. So safety considerations still have to be observed by any agent. So therefore, the minimum green and yellow times are considered part of the transition function, not the action space. And any required yellow signals are also automatically inserted via the transition function as well. So the agent can't choose to optimize the signal by ignoring safety constraints. So in terms of objectives, for optimizing intersections, average delay caused by the intersection is usually the goal. However, this can lead to unfair cases when low volume arterial roads are deprioritized, leading to excessive individual delays. Still, most studies, including ours, sets this problem aside for future work. We don't typically see it happen in the scenarios we examined, so we would have to set up particular tasks to see this problem occur. So even considering only average delay, measuring delay caused by an intersection in real time is difficult when moving to the multi-agent system, as the delay can be imposed by one intersection on another through poor coordination of the intersections. So for this reason, we use waiting time for our reward function, as it can be measured in real time at each intersection individually. And we found that it's a decent approximation of delay when measured in hindsight over all of the intersections. Finally, the transition function is determined by the traffic simulator. Unfortunately, for the time being, real-world experiments are rare due to the cost and regulatory laws in place. So moving on to the multi-agent setting, a number of domain-specific algorithms have been proposed. However, these algorithms were difficult to evaluate as they used different underlying traffic simulations with varying degrees of complexity, and they lacked any open source implementations. So two of these algorithms are the feudal multi-agent A2C algorithm and MP light, which stands for max pressure light. The feudal multi-agent A2C, as its name implies, is based on A2C, and MP light is based on DQN, with some slight modifications more specific to traffic signal control. So since they were difficult to compare, we implemented a benchmark that was published in the benchmark track at NERSC. So the reinforced signal control benchmark relies on the simulation for urban mobility traffic simulator, which has been utilized in traffic research for over 20 years. It includes a complex car driving and intersection model capable of scaling to entire cities. Within this framework, we extracted 6 tasks from 2 published traffic models of real cities in Ingolstadt and Cologne, Germany. 2 of the tasks are single agent, and the remaining 4 are multi-agent tasks. I'll talk more about those tasks when I move on to the slides near the end. But for now, we implemented some static classic controller baselines, fixed time, max pressure, and the queue length greedy method, somewhat similar to the max pressure one. So in addition to those, in addition to the two learning algorithms mentioned before, we compared two straightforward learning approaches with a simple state modification based on convolutional aggregation layers. So moving on to the results, we found somewhat surprising results as we assumed that the domain dependent methods would work better. So in these graphs, delay is plotted on the y-axis, and the lower delay indicates better performance. So you want the line to go down here, not up like in usual RL papers. The static controller performances are plotted with dashed lines. There is some variation in them, but here they're just averages. So in most of the tasks, we found that the straightforward DQN or PPO controllers outperformed the other learning algorithms, despite the results reported in their respective studies. So you'll notice FMA2C and IPPO here are represented as a single point. This is due to these algorithms requiring significantly more time to converge over the Q-learning based algorithms, which it can be optimized or can be reduced, not optimized, but with hyperparameter tuning. But here we use the hyperparameters that were suggested in the original paper or implementation in the case of IPPO. So given these results, we validated our implementations of the domain-specific algorithms on the scenarios used in their studies, because they claim that they outperformed basic methods like DQN and PPO. So we went and validated them back on their original environments. And we found that the reported results were accurate for those simplified environments. However, in the more realistic scenarios pulled from these published traffic models in each of these cities, they clearly don't perform as well as they might. And another aside here, you'll see that MP Lite is both in purple and in yellow. So MP Lite in its original implementation has a fairly simplified state space. It really only uses the Q length at each intersection. So in the yellow MP Lite line here, we ran MP Lite with a full state assumption, where it can see like all the waiting times of the cars and how many are approaching and how many are waiting. And only in one of the tests did we find that it outperformed the original implementation. So these results highlight the importance of experimental settings when setting adjustments made to standard RL algorithms for domain-specific applications. The experiments in the original papers were too simplistic to give an accurate assessment of the proposed algorithms. So following a traffic signal control benchmark, we discovered your lab's more general cooperative multi-agent benchmark, published concurrently with RESCO at NERCS. I'll give a quick summary here of it. The extended MARL benchmark implements 9 domain-independent algorithms, including 3 independent and 6 centralized training, decentralized execution methods. The algorithm's performances were compared across 5 environments with a total of 25 different tasks. In a similar vein to our results in RESCO, straightforward independent methods performed well in all of the tasks, though not the best in all of them. But in 19 of the 25, an independent method obtained the best performance, so like not significantly different from the best performance. So we wanted to examine if domain independent algorithms could optimize traffic signal control beyond that of the domain specific algorithms we examined in our benchmark. So we made some slight modifications to MARL. In traffic signal control, parallel environment instances is not possible in the real world. So any algorithms assuming this were limited to a single instance. Additionally, the time frame for optimization is typically over a shorter period, a matter of tens of episodes instead of thousands. So policy rollouts were adjusted to operate on a period of steps instead of number of episodes per rollout. So we can see here that each of the 5 environments has a different observability assumption, reward sparsity, number of agents, and an identified main difficulty in ePyMARL. So the where RESCO fits into this, observability is partial because each intersection is assumed to not be able to see all of the roadway between itself and another. The reward sparsity is dense because we do have a constant signal for the waiting time for every car at a signal. And the number of agents is significantly higher. So in our multi-agent case, the minimum number of agents is 3, and the max, well, not really significantly higher, but it goes from 3 to 21. So it's a little bit more than the StarCraft environment. And the main difficulty for our experiments is coordination, though the traffic signal control in general is a non-stationary problem, because as I mentioned at the beginning, when construction happens or say an event like a football game or something, would change the conditions under which the agent were trained. So these are the results we got of running the standard algorithms. We did run all of them, but here we just pulled out the best performances because, well, the graphs would get quite messy. And the static methods are again in a dashed line, but they are only showing the best static method for each of the scenarios. And the IDQN here isn't the independent DQN implemented in the ePyMARL benchmark, though we did run that as well. But we found that the DQN implementation from RESCO performed slightly better. So that's shown here. So what we found in each of the tasks is that DQN typically still performs better than the domain independent algorithms. And to tune the hyperparameters of these algorithms, we went back to the simplified validation scenarios we had for the MP-Lite and FMA2C scenarios and tuned it on those simplistic intersections, as that would be sort of an exemplary transfer situation. But we found that those tuned hyperparameters didn't actually outperform the parameters that were already set in ePyMARL for the original experiments. So the results here are from those original settings. So here on the right side, we can see the Cologne corridor blown up. So in this map, there are 3 intersections only marked with the red boxes that are controlled by lights. And between each of the intersections, there's other intersections that aren't controlled by any agent, and vehicles enter and exit on these lanes as well. And this Cologne corridor scenario presented the most difficult coordination task of any. You can see in the graph, in the top left graph, that the fixed time controller still outperforms DQN most of the time. And the reason for this is that in a tight corridor like this, the settings for a classical controller will be set up for a green wave, so that once a car passes one intersection, the next intersection gives a green light just as that car is reaching the next intersection, which, as far as we know, is the optimal behavior for corridors such as this. So here's the Ingolstadt corridor. It has 7 controlled signals with fewer intersections in between where vehicles would leave the system. And you can note here that the intersections are heterogeneous, that they aren't similar. So the agents have different numbers of actions, different state spaces between them. So you can't just apply one model to all of them and hope to see the same results, which some environments you can have very homogeneous agents. So the results for this one is in the bottom left graph. And here DQN outperforms even the static controller. And we see that actor critic methods fail to really perform down at the Q-learning method levels. So the Cologne region and the Ingolstadt region aren't these tight coordination problems. They're more spread out systems. And here I think it's 8. There's only 8 signals in this region. I'm sure you count it too. Oh, I guess I have it on the graph too. But here again, DQN is the best method, which is surprising because a lot of work has been put into making these multi-agent algorithms perform better and coordinate better. And here's the Ingolstadt, the largest map. It's scaling up to many kilometers of area in the region. And there's 21 traffic signals, and you can see that the Ingolstadt corridor system is present in this region in the bottom right of the map. And here, once again, the straightforward DQN approach is outperforming the more complex coordinated methods. So thanks for listening. In summary, the multi-agent traffic signal control problem is a difficult problem for MARL agents, as it presents a partially observable environment with heterogeneous agents, and the agents have varying impacts on each other due to the distances between them, which in the graphs that you just saw could vary greatly. So in like the Ingolstadt region, an agent in the bottom right of the map would have very little impact on the top left, almost to the point that it would have no impact. So modeling the behavior of that agent would not be beneficial. And it also presents a high level coordination task for the corridor scenarios in specific. And in the RESCO environment, we found that the state-of-the-art algorithms, the FMA2C and MP-Lite algorithms, they performed well in their simplified environments, but they failed to perform in the more realistic scenarios we extracted from those traffic models. And the code for RESCO is all open source at that GitHub page, and we've updated it so that anyone can go and run the EPI-MARL benchmark algorithms on our task. Thanks for listening in.
Okay, thank you very much, James, for the presentation. We'll open the floor for questions now. So if you have any question, feel free to unmute yourself, or you can also ask them on chat.
Yeah, I have a question. So in your last slide, you have mentioned that independent methods may be more robust to realistic scenarios. So what kind of realistic scenario do you use?
So by that, I mean these scenarios we pulled out of the modeled cities. So there was quite a lot of effort put into creating these Ingolstadt and Cologne city models by the authors that published them to capture the actual traffic demands and that like recorded traffic demands within the city and model the behavior throughout the day. So these are more realistic than say, unfortunately, I don't think I have a image of it, but some of the scenarios are MPLite and FMA2C showed good results were on simple grids. So while we have like maybe New York City, there's a nice grid layout of all the intersections with substantially similar intersection designs. So you can see here on the right a bit. A lot of cities aren't laid out in this nice grid though. So the coordination problem is a little more difficult. And also in MPLite's case, it was modeled in the city flow simulator instead of the SUMO or simulation for urban mobility. And in that simulator, there's some somewhat relaxed assumptions regarding the complexity of say driving or intersection modeling. So within an intersection, how the cars drive, they don't drive perfectly. They speed up and slow down. It takes time for them to accelerate once they stop at the light, that kind of stuff.
Okay, thank you very much. Another small question. So you have plotted the figures, how the delay parameter changes for different algorithms. I don't quite understand what the definition of delay. Delay related to what? How do you define the delay? Yeah.
So this is on a road. Well, we know the entire route that a vehicle takes through the simulated area, and we know the speed that's allowed on that road. So it's versus the free flow delay. So it'll take a vehicle, say 20 seconds to get through the entire map with no other vehicles on it. So then the delay is anything over that 20 seconds it would have taken to get to the end. So
okay, that means the
overall vehicles.
Okay, that means the reference value is calculate when the vehicle is driving on the road without any other vehicles.
Right. Yeah.
Okay. Thanks.
And also not stopped by the traffic light at all. Basically, just assuming it's as if it were like a highway with nobody else on. Yeah.
Okay. I'm not sure. I still have time to ask the last question, Samuel, or maybe I should give.
Oh no, you do have. We do have plenty of time. We have until 4, so that's completely fine.
Okay. Thank you very much. Yeah. So I'm wondering. So you apply multi-agent representation for the traffic signal control. So if there are multiple or a number of vehicles in the section, or so I think the computational cost could be very high. I'm not sure because in a bigger intersection there could be multiple lanes in each direction, and on each lane maybe 6 or 5 vehicles. So there could be 20 vehicles at the same time in one intersection. I'm not sure whether it's possible to apply one single multi-agent representation to handle such large scale agents. I'm not sure.
Yeah. So In this case, the agents are following a simple, well, relatively simple driving model. They're from like a high level. They're not assumed to be agents themselves, like controlled by RL here. But you're right that there are in our simulations, I think goes up to thousands of vehicles moving at the same time. So if we were to control all those vehicles, but in these experiments, the vehicles are assumed to have a route that goes through this area, and they will follow that route according to the driving model that's implemented in Sumo, which it does try to model human behavior, but not as closely as it might. It can be improved. And actually, there's some work that has been done on improving that driving model, allowing RL to optimize it so that it more closely models the actual behavior of humans driving. But this is only for the actual traffic signal controller, not the individual vehicles themselves. So in that case, the computation scales up mostly just in terms of the number of lanes, not with the vehicles. The vehicles would just increase a number in the state space rather than the size of the state space. But the state space can still get very large because, well, you can have hundreds of intersections in one system with I think like 20 some lanes is the largest that I've seen modeled per intersection. So it can still get quite large, even though the vehicles themselves don't scale it up.
Okay, yeah, thank you very much. Thank you.
Are there any other questions from the audience? Hey, James, can you show the later graphs, the ones that are newer?
Yeah.
Are those with just one seed, or are you just showing the mean?
Yeah, so these are just the mean.
Oh, okay.
I think it was 5 seeds. Yeah.
Yeah, I was a bit surprised that IDQN is still like outperforming the other methods.
Yeah. Same. We were too. But we really did expect the other algorithms to perform much better. And maybe they could with better hyperparameter tuning. Like
yeah.
But the transfer between like simulation to real hasn't really been studied too much for traffic signals. So proposing that you be able to tune the hyperparameters on the exact traffic signal you have is not so realistic in an actual scenario without sim to real, because nobody's going to allow you to have terrible performance at their intersection for a month or two while you work out hyperparameters.
No, yeah, of course, not feasible at all. Yeah. Yeah, no, we were just discussing about like yeah, how surprising it is that just this independent methods still outperform the inheriting MARL approaches. But
Yeah. Sometimes the cooperative ones do they do better, but it would be expected that maybe they would do better. Or at least I expect they would have been more impressive. I suppose that's where the future work is to do that.
Yeah, and probably something is related more to the application. I don't know.
Yeah. So with the traffic signals, so I mentioned like the green wave in the Cologne corridor here. So actually seeing RL produce that green wave, we haven't gotten that yet. So there's definitely room to improve with more structured for domain specific approach here.
Yeah.
one of the guys was also asking if perhaps for the multi-agent RL you will need like more training. I don't know if you have tried to train for longer times.
So yeah, we have. It didn't really result in any better results. So we did some hyperparameter tuning to try it, and one of the hyperparameters was length. Here we're using just 100 episodes because, well, you need to reach a pretty good performance if we're going to assume that we can just run this on a real intersection.
Yeah. You don't want to have
pretty quickly, right? Yeah. So, but also learning from demonstrations can bring down that initial poor performance. So it can allow for longer training periods, but we didn't actually find much better long-term training. Though if we stretch it out and apply like learning from demonstrations, it might. So that's where we're going with it now.
Okay, yeah, thanks.
James, just a quick question on the variance that you see between seeds in these algorithms. Did you assess that, or were you surprised by?
So there actually is fairly significant amount of variance between the seeds, but not that much. And by that I mean it's not enough variance to really say that there's it's working on a different traffic demand between one seed to another. Though we do plan to implement like non-stationary tasks because that is definitely something where RL may have an advantage over standard controllers. And really that's what we need to displace is the standard controllers. Because we tell them, hey, you can do 5% better to a government, they might see, oh, it's going to save a lot of time over a long period. But if there's much more efficiency to gain in solving the non-stationary aspect.
Yeah, that makes sense. Yeah, thanks. I think we've got a question from Andres, from Alain.
Yeah, hello, could you hear me?
Yeah, we can hear you.
Yeah, I have one question. Could be any kind of correlation between the number of intersections and the performance that you obtain? In the sense that, I don't know, maybe it's only on this slide because I'm not able to see on the other ones, but it seems that the more intersections you have, the worse that it performs. At least when you compare multi-agent reinforcement learning approaches in comparison to the IDQN approach. So it could be an issue regarding the scalability.
Yeah. So we didn't examine it beyond the 4 we have here because it actually takes a large manual effort to set up one of these maps, primarily because you have to set the downstream intersection. So for instance, in this map, you have to clarify that this one, the intersection, I'm not sure if you guys can see my cursor, hopefully.
Yeah.
So the left, oh, you can, okay. So this intersection here, you have to manually define that this one is to the right of it, it's downstream to the right, and this one's to the right of this one. So as that scales up to like 20 of them, it becomes a headache. It can be automated. We haven't gotten there yet because it's just me working on this. So yeah, it might be with scale, but it's hard to say from just the 4 scenarios we have here.
Okay, yeah, because I was doubting because VDN seems to work like kind of okay when you compare with IDQN. But for example, MADDPG or the other multi-agent approaches, they seem to have some difficulties in order to learn. So maybe using something to solve these scalability issues, because indeed, as far as I have understand you, any of those intersections is an agent. So probably if you use, I don't know, something like attention mechanisms or something like that in order to reduce the scalability issues may help in the performance of these setups.
Yeah, okay. Good suggestion. Thanks.
Okay, are there any other questions? Okay. Well, thanks, James, for coming, and thanks for everyone for the discussion. That was very interesting. And I think I will stop the recording now. And yeah, I hope to see you again one of these days.
Yeah, thanks for inviting me. It was great. Good questions.
Cheers. Bye. Take care.
Bye-bye.
Thank you.